Well, we've already embarked upon our journey through gases and liquids. Now we're going to take a look at solids and other modern materials. Just an FYI, there are 6 supplemental videos I have listed in Canvas in the modules under Chapter 12. Check them out for further details on the following subjects that you will see in this PowerPoint. Recall that as you go from a gas to a liquid to a solid, the atoms are moving less. They're more ordered. Because of that, there are certain characteristics of solids. They could be hard, they could be soft. Some conduct electricity, some don't. Shapes can be manipulated, sometimes they can't, and they're brittle and they just resist change and crumble and break. But all these physical properties are dictated by the types of bonds that hold them together. And there's actually different kinds of solids we're going to explore in this video. So here are the 4 types of solids: metallic, ionic, covalent network, and molecular. Metallic solids are held together by delocalized sea of collectively shared valence electrons. Remember that in metals, the electrons are delocalized. They're not necessarily around just one nucleus. They're just free floating from nuclei to nuclei. And that makes them really great at conducting electricity and heat. They are strong. They're not very brittle. We can bend them and use them in all sorts of things. Ionic solids are held together by that electrostatic attraction between cations and anions. In regular chemistry, we talked about ionic being elements that give away and steal electrons. Ionic solids do not conduct electricity well, and they're very brittle. Now, dissolved in water is a different case, but as a solid, not so much. Covalent network solids are kind of tricky. They're held together by this extended network of covalent bonds. They're solids, they're very, very hard, they're usually semiconductors. And so sometimes if you're doing a lab and you're evaluating different bonds, you might mistake covalent network for metallic or maybe even ionic, just because they're so kind of strange and different. Molecular solids are held together by intermolecular forces, which, if you remember, are pretty weak, and they tend to be soft with low melting points. At the very end of this video, we'll talk briefly about polymers and nanomaterials, neither of which fit into really these 4 types of solids. There are 2 basic solid structures. One is called crystalline and the other is amorphous. In a crystalline solid, the atoms are arranged in this very ordered repeating pattern. They have flat surfaces with definite angles toward each other, highly regular shapes. Examples would be sodium chloride, quartz, and diamond. Amorphous solids, it's exactly what amorphous means. Am means without, and morph means shape. These lack that order that crystalline solids have. They kind of have a structure like liquids, except that they lack the freedom to move like in a liquid. They don't have well-defined faces and shapes. Examples of amorphous solids are glass, rubber, obsidian, which is volcanic glass. Now, over the years in science, you've heard us talk about monomers or building blocks. Some that you will recall. Carbohydrates, their monomers are sugars. Proteins have amino acids. DNA have nucleotides. Well, in solids, we have something called the unit cell. And the unit cell is this relatively small repeating unit that is made up of a unique arrangement of atoms that basically embodies the structure of the solid. These unit cells can be stacked over and over again 3-dimensionally. And the structure of crystalline solids is defined by the size and the shape of the unit cell, along with the location of the atoms within that cell. Crystal lattice. This is the structure of solids, and it's going to remind you a little bit of geometry class here, so hang with me. A crystal lattice is the geometrical pattern of points on which the unit cells are arranged. It's this scaffolding for the crystal structure, but not in reality. What you need to know about crystal lattice is we have these things called lattice points. You can see those are those black dots in the diagram. And each lattice point has an identical environment. And of course, just like in geometry, there are vectors. Each lattice point has two vectors. So if you look at the one point, they have an arrow coming out labeled A and another one labeled B. And then you have the parallelogram, and it's formed by the lattice vectors, which defines the unit cell. And I just bring this up because you're going to hear me talk about lattice points in just a moment. So I'm trying to think of a really great analogy to explain this, and I'm kind of lacking, but instead of Legos, if you ever worked with the connects stuff, kind of like Legos, but it allows you to connect pieces together and you can create a two-dimensional piece. You can add layers and build it three-dimensionally, and that's kind of what we're looking at here. Two-dimensionally, unit cells take on only one of 5 shapes, and you can see those shapes in that diagram, and feel free to go and look in your book for more information on that. You're not going to see pentagons and polygons because they cannot cover space without leaving gaps. And again, if you aren't sure about these shapes and these angles and all that, there's plenty more information within your textbook. But three-dimensionally, we start to get a real version of what the crystal looks like. And a 3D means we're looking at 3 lattice vectors along the x-axis, y-axis, z-axis. They label them A, B, and C, that make up a unit of 7 possible 3D shapes. You can have cubic, tetragonal, and so on and so forth. Again, you can look these up online. You can see them in the book if the picture's not real clear to you. But just to give you an idea of all the different ways crystals can look. Let's look a little bit more at this 3D lattice thing. The first we have is called primitive lattice. Now, on the previous slide, those 7 shapes are what we call primitive lattices. And all we're talking about is that the lattice points are placed at the corner of a unit cell. And I'm talking about the corners like right here. You see that right there? Maybe that's not the best color to use. That corner right there. That's what we're talking about. And then there's 2 kinds of centered lattices where we have additional points, not just at the corner. The first one is abody-centered. So we still have these lattice points at the corners, but now we have one that's in the middle of the cube. So imagine you have a box, and like right in the middle of that box, obviously there's nothing in there, it's open, but there's a point. And we're going to talk about that point in a minute. And then we have one that's called the face-centered cube. So we still have the ones on the corner, like we've been talking about, the lattice points. And now what we have is we have points on the center of each face. Well, a cube has 6 faces. So if you have a face, right in the middle would be 1 on each of them. So there'd be 6 face-centered pieces. So we're almost to getting to the shape of solids, but we're not quite there yet. We have to talk about defining the crystal structure, filling the unit cell. Like just exactly how do those atoms fit in this space? So the lattice itself does not define crystal structure. We need to associate atoms or group of atoms with each point. If a solid is made up of an element, the simplest structure exists. That is, each atom lies on a lattice point. Most crystals, though, are made up of groups of atoms called motifs, and this motif is associated with a lattice point. It starts to get a little bit more complicated. But there are 2 points you need to know about crystals. 1, no atoms lie on lattice points, and bonds can form between atoms in neighboring unit cells, and the bonds need not be parallel to the lattice vectors. So there's a whole lot going on when you start talking about why are solids so strong. Because not only are they interacting with atoms next to each other, but then you have to start looking 3-dimensionally and what's happening above it, below it. Gets kind of complicated. But if it's just an element, very, very simple shapes. Crystals are a little bit more complex. We're going to talk about 4 different solids. And the first one is going to be metallic solids or metals. Obviously, they're made of metal atoms. the metallic bonding occurs because the valence electrons are delocalized. That means they're not centered just around one nucleus. They can move freely from nuclei to nuclei to nuclei in this sea of electrons. And I always use the analogy of I have an empty room and I've got four of those kind of like waist-high tables. And on this table, I've got brownies. And on this table, I have nachos. Over here are beverages. And over here are, I don't know, pretzels. And people can just come into my party and they could just flow from table to table to table and get what they want. That's kind of like a sea of electron. Metals have luster, so they're shiny. When you feel them, they feel cold. They have high thermal and electrical conductivity. Do not try this at home, but if you were to put a fork in an outlet, you're going to find out about that conductivity. Or put a metal spoon in a pot of boiling water and just leave it for a while. It's going to get pretty hot. Metals are malleable. We can bend them. Now, granted, sometimes you have to heat them up. They're also ductile. We can draw them out into a wire. And their atoms can slip past one another. And there's three kinds of structures. They can form primitive lattice. Lattice points are placed at the corner of each unit cell. They can be body-centered, one lattice point at the corner of each, and then one that's right in the middle. And then, of course, you have the face-centered, which means you have atoms at each corner and then also in the center of each face. And I know it's not the easiest to see here, but if you look, if I can make my pen work here. So right here in the primitive, we have 1, 2, 3, 4, 5, 6, 7, hard to see, but 8. There's only 8 atoms and they're all at the corners. In the body-centered, you have those 8 again, 4 there and 4 in the bottom. I don't know if you can see it though. There's one smack dab in the middle of that square. And then with the face-centered, again, you have all of them on the corners. That would be 8. And then you have them on the face of each side, and there are 6 sides. And you're going to see what this looks like here in a moment. So this is where it starts to get kind of complicated. There is sharing of atoms going on between unit cells. And if an atom is on a corner, it's actually going to be shared among 8 different unit cells. And I don't know if you can see it here. I'm not the best at visualizing, but that right there is just 1/8 of an atom. So if you can picture another square next to it and above it and over here three-dimensionally, that one atom is being shared amongst 8 different unit cells. So if you think about a primitive lattice structure, there are 8 corners. If there is 1/8 of an atom in each corner, 1/8 times 8 is 1 atom. So in a primitive cube, there is a total of 1 atom. In the body-centered, a little different. You still have the 1/8 at each corner. 1/8 times 8 makes 1 atom. But you also have a whole atom right in the middle in the body-centered. I don't know if you can see it in there, but there's a whole atom in there. For one of my graduate classes, I had to draw this. I can't visualize. I cannot draw, but I made it work. So if I can do this, I promise you, if you just start drawing these, you can see this a little bit better. Now the face-centered is a little bit different. You have the 1/8 on each corner. So 1/8 times 8 is 1 atom. And then on the face of each one, you have half an atom. So you have 1/2 an atom per face. There are 6 faces. 1/2 times 6 is 3. So you have 3 atoms on the faces, you have 1 at the corners. So if you have a face-centered cubic metal, it adds up to 4 atoms altogether. To really determine and look at why solids are so unique, you have to look at something called close packing. And it's how the atoms in metals are arranged. And this is because they are very, very closely packed due to the shortage of valence electrons and the fact that the electrons are shared. Well, each type of packing has what is called a coordination number of 12. In other words, Each sphere, and it's really hard to see until you go and look at a picture in the book or online, but each sphere has 12 equidistant neighbors to it. 6 in the same layer, 3 above and 3 below. And again, I'm not a visual person, but if you look at, let's just pick one of these atoms right in the middle. I'm going to switch to yellow here. Let's look at this one right here. Okay, where are the 6 around it? 1, 2, 3, 4, 5, 6. There are 6 of its neighbors. Now this is where it becomes difficult for me to visualize, but if you could picture another layer above it, there are 3 in contact with that particular atom. There are also 3 below it. So each atom has 12 neighbors that are nearby and touching it, if that makes sense. Well, we can't talk about metals without addressing alloys, and there are 4 different kinds. First of all, an alloy is just a material that contains more than one element, but it has the characteristic properties of a metal. The first one is called substitutional. This is a homogeneous mixture, so it looks like you just have one metal. And this forms when 2 metallic components have similar atomic radii and chemical bonding characteristics. These solids are also solid solutions. The solvent is the majority component and the solute would be the minority component. But think about what the word substitute means. If I got sick and needed to go home and they had to bring in a substitute teacher, it's going to be another adult. They're not going to bring in a kindergartner to substitute. You're playing soccer and you need a substitute on the field. You're not going to bring in a ballerina. Highly entertaining, but it's not what you're going to do. So if you look at this picture here, you can see that both the zinc and the copper are about the same size. The next one next to that is called interstitial, and that literally means in between the spaces. So here we're going to add more atoms, but they're going to be really small in size. See it right there? And they're going to fill those spaces in between the atoms. And it causes the properties to be a little bit different. The lattice here tends to be stronger and harder and less ductile because you filled up those spaces so the atoms can't just move around each other as well. A heterogeneous alloy, the components are not dispersed uniformly, and the properties really depend upon the composition and the manner in which the solid was formed. Did you rapidly cool it? Did you slow cool it? That makes a big difference. Intermetallic compounds are compounds, not mixtures. They have definite properties and compositions cannot be varied. Types of atoms are ordered, not randomly distributed. This leads to structural stability, higher melting points, but they are more brittle. But they're very useful in things like jet engines and razor blades and superconductors and MRI scanners and so on. For the most part in this class, we focus on the substitutional and interstitial. So just remember that substitutional means you're substituting out some of the atoms, but you're substituting, so they're going to be similar in size and property. Interstitial means in between the spaces. So you're going to add an atom, usually carbon, that's a whole lot smaller that can fit in between the spaces. Let's wrap up our discussion on metallic bonding. Remember, it's an electron C model. There is an array of metal cation ions in a sea of valence electrons. So you can think of like these positive nuclei, and you've just got the sea of negativity just floating around it. The electrons remain around the cations because they're attracted to them. They are uniformly distributed, so you're not going to find a bunch of electrons in one location more so than another. The electrons are very mobile. They move freely. This is why they conduct both heat and electricity so well. Metal atoms form bonds to many neighbors. This allows changes in positions of the atom. Metals are reshaped. And there is a whole nother piece to metallic bonding called molecular orbital theory. And the cool thing about that is it's kind of complicated, but it explains some of the unique properties we see in different bonding, but we're just not going to discuss it in this class. Let's go ahead and touch on ionic solids. These are held together by the electrostatic attraction between cations and anions. You remember, Something is giving away electrons and something's taking electrons. Sodium will give away an electron and chlorine will take it to make sodium chloride. Ionic solids have high melting and high boiling points. If you put some sodium chloride in a test tube and heat it over the hottest temperature Bunsen burner we have, it's not going to melt. They have very strong bonds, and that is dependent upon the charges and the sizes of the ions. We've talked about this before. Small ions can be closer together. The higher the charge, like aluminum with a 3 positive, oxygen with a 2 negative, are going to stick together stronger as well. Ionic solids are insulators because the electrons are not delocalized. They're found around the anion, so they're not just freely flowing and being able to conduct electricity and whatnot. Ionic solids tend to be brittle due to the repulsive interactions between ions of like charges. And atoms line up like this: cation, anion, cation, anion, which makes sense. Positive, negative, positive, negative. So how are ionic solids different from metals? Well, the atoms have different radii and opposite charges. Cations are smaller than anions because they've lost electrons. And remember, every time you lose an electron, the electrons out here repel less and they get closer. You lose another electron, they repel less, they get closer together. You can also think of it in the sense that you're getting rid of something. So, if you chop off your arm, you're going to get smaller. Coordination numbers are much smaller than metals, so you don't have as many atoms in contact with each other. Most favorable structures are those where the cation and anion distances are as close as those permitted by ionic radii, but anion and cation distances are maximized. So in other words, they are arranged so that the attractions are the strongest, but the repulsions are farthest apart. There are two kinds of structures with ionic solids: the primitive cubic lattice and the face-centered cubic lattice. And what makes for the most favorable structure are the relative sizes of ions in stoichiometry, the relative numbers of cations and anions, and that will actually dictate what the structure looks like. Let's look at the last two solids together. First, molecular solids. These consist of atoms or neutral molecules that are held together by the intermolecular forces like dipole-dipole, dispersion, and hydrogen bonds. Molecular solids are soft. They have low melting points. The properties really depend on the strengths of the forces between the molecules, their molecular shape, how tightly the molecules can be packed together. Covalent network, on the other hand, these atoms are held together by a large network of covalent bonds. So you don't just have small amounts of covalent bonds, you have lots of covalent bonds that are just kind of holding everything together. The solids are much harder, they have much higher melting points than molecular solids, and sometimes they're kind of misleading. You might actually mistake a covalent network for a metal or an ionic solid when in reality they're not. Examples of covalent network are diamond, graphite, silicone, germanium, quartz, and so on. There's quite a few examples if you want to research them. They're pretty fascinating. Metals are conductors, but network covalent solids are semiconductors. What do we mean by that? Well, it conducts electricity, but not as well as metals. They also don't tend to get hot, which is a great feature if you want to put it in your computer. You want to conduct electricity without, melting your computer down. Silicone and germanium are some great examples semiconductors. Silicone is similar in shape to a diamond, and its conductivity increases as the temperature goes up. There are two kinds of semiconductors. One is just elemental, and typically this is just one atom, usually from column 14. We do have semiconductors that are compounds, and again, compounds have two or more elements. Electrical engineers can manipulate both the orbital overlap and bond polarity to make semiconductors. And there is one thing that they do called semiconductor doping. What they do is they add a small number of impure atoms to a material to increase the conductivity. There's two kinds. One is called N-type, and this is by adding an element with one more valence electrons than the element you currently have. So let's say you've got something in column 14, you would pick an atom from column 15 because it has an extra valence electron. The p-type semiconductor doping is where you add an element with one less valence electron. So if your original atom is from column 14, you would choose something from column 13. And without getting all into it, because we didn't really talk about all of this and like valence bands and all this kind of stuff, but depending on which one you do, p-type or n-type, it allows for electrons to start moving throughout, and that's what allows for the conductivity. It really is very, very cool. There's some great videos out there on semiconductors you might want to look up. Let's briefly discuss what a polymer is. You guys know poly means many, and that's pretty much all we're talking about here. These are just molecular substances of high molecular weights formed by polymerization, joining together of monomers. You've heard this with like proteins, hooking the amino acids together to make a protein. We have lots of natural examples: starch, cellulose, wool, leather, silk, natural rubber, and of course there's a bunch of man-made ones: plastics, nylon, polyester. There's so many different kinds of reactions that occur to make polymers. One is called addition polymerization, and that's where monomers are coupled through multiple bonds. And then condensation polymerization, it's where you take two monomers and you join them together by eliminating water. And shoot, we've been talking about this since y'all were in biology. Copolymers are formed from two different monomers, and they have some pretty unique properties like flexibility, long chains, and they tend to be amorphous. And that's all we're going to touch on polymers. And lastly, there is an entire field out there on nanomaterials. Really small little things. Just know that this is a hot area of research, and they're being used to develop electronics, batteries, solar cells, and even medication. We're not going to look a whole lot at it because a lot of this is based around molecular orbital theory, and at the timing of this video, I'm teaching AP chemistry, and the AP board says we don't need to study molecular orbital theory. If we do down the road, I will add it in and redo the video. But for now, just know that nanomaterials is pretty cool, and it might be something you want to further look into and maybe even pursue in college.